Good morning, everyone. Thank you for joining today's presentation. My name is Feng-Cheng, and I am presenting on behalf of our research team from Feng-Cheng University. Our paper is titled An Improved UNet for Multi-Object Detection and High-Resolution Aerial Imagery. This work is a joint effort by Feng-Cheng, myself, Hong-Ren Liao, Chih-Cheng, and Tz-Feng. The research was supported by the National Science and Technology Council of Taiwan. Over the next 20 minutes, I will walk you through our motivation, proposed methodology, experimental results, and future directions. Let's get started. Here is the outline for today's talk. We begin with the introduction, covering the research background and our three main objectives. Then we review related literature on UNet variants and remote sensing segmentation. The third section describes our methodology, including the ISPRS datasets, our proposed dual ASPP architecture, and the composite loss function. In Section 4, we present experimental results from both ablation studies and comparisons against state-of-the-art models. Finally, we conclude with a summary and future work directions. Let me start with the motivation behind this research. High-resolution aerial imagery has become an essential data source for large-scale urban monitoring, supporting tasks such as carbon sink inventory, land use analysis, and infrastructure management. However, traditional manual interpretation is slow, costly, and inconsistent across different operators. While deep learning, especially convolutional neural networks, offers a promising solution, applying these models to complex aerial scenes presents unique challenges. We face extreme scale variation, where buildings and small vehicles coexist in the same image. We also encounter complex backgrounds with heavy shadows and similar textures. Additionally, class imbalance is a persistent problem, where small objects like cars and tree crowns are underrepresented compared to large classes. These challenges motivate the design of a specialized architecture, which we will describe in the methodology section. Based on these challenges, we define three concrete research objectives. First, we aim to develop an improved multi-target semantic segmentation method specifically designed for high-resolution remote sensing imagery, going beyond the limitations of standard UNet. Second, we want to simultaneously achieve accurate feature extraction for both large-scale structures, such as buildings and roads, and small-scale objects, such as vehicles and individual trees, within the same scene without sacrificing one for the other. Third, we want to mitigate class imbalance, where small objects like tree crowns and cars are routinely missed by models that are dominated by majority classes. These three objectives collectively drive the architectural and training strategy choices that we will describe next. Before presenting our method, let me briefly review the most relevant prior work. SAUNet, proposed by Fan et al. In 2022, integrates ASPP and a spatial attention module into UNet, achieving improved multi-scale land cover classification. However, its attention mechanism is primarily applied in the decoder and does not fully address the gridding effect of standard ASPP. ASPP UNet, by Cui et al., replaces max pooling with strided convolutions to preserve fine details, but focuses mainly on the encoder side. The multitask UNet by Freudenberg et al. Simultaneously learns binary masks and boundary maps, significantly improving tree crown segmentation. While these works advance UNet for remote sensing, none of them jointly address the bottleneck-level context modeling and decoder-level detail reconstruction that we propose in our dual-module design. For our experiments, we used two standard benchmark datasets from the ISPRS 2D Semantic Labeling Challenge. The Weingen dataset was captured over a small German town at 9 cm ground sampling distance, using near-infrared, red, and green spectral bands. It contains 33 image tiles averaging 2,500 by 2,000 pixels, featuring dense residential buildings with strong shadows and sloped roofs. The Potsdam dataset represents a historic city at 5 cm resolution using standard RGB channels. It contains 38 large-scale tiles at 6,000 by 6,000 pixels, with large building blocks and dense mature trees, causing significant occlusion. Both datasets share 5 semantic classes: impervious surfaces, buildings, low vegetation, trees, and cars. To make these large images manageable for deep neural networks, we apply a sliding window approach to crop them into 256 by 256 patches, expanding the Vaihingen set to 2,254 patches and the Potsdam set to 20,102 patches. Now let me present our proposed architecture. We call it the improved UNet with dual lock mechanism. The classic UNet uses a symmetric encoder-decoder structure with skip connections. Our key innovation is the introduction of two ASBP-based modules at different positions in the network. The first is CESBP, placed at the bottleneck, which captures global multi-scale context using dense dilation rates of 1, 3, 6, and 9. The second is RASBP, placed in the early decoder layers D3 and D4, which performs fine-grained boundary refinement using microdilation rates of 1, 2, and 3. Together, these two modules form what we call the dual lock mechanism. CESBP locks in global semantic consistency at the deepest feature level, while RASBP locks in local geometric precision during the upsampling reconstruction. This two-stage design ensures that the model captures information at all scales without suffering from feature discontinuity. This slide shows a visual overview of the dataset preparation process. We apply the sliding window cropping method to transform large orthophotos into standardized 256 by 256 pixel patches. During this process, patches that fall outside valid image boundaries are automatically discarded to prevent edge artifacts. The result is a substantial increase in training data diversity, giving the model exposure to a wide variety of spatial contexts, object scales, and background textures. This diverse training set is critical for learning robust multi-scale features and for ensuring that batch normalization remains stable throughout the training process. Let me now explain the design principles behind our two ASBP modules in more detail. Standard ASBP uses sparse dilation rates such as 6, 12, and 18 to rapidly expand the receptive field. However, in high-resolution aerial imagery, this creates a well-known gridding effect, where the sparse sampling pattern generates information blind spots. This is especially harmful for small, closely spaced targets like parked vehicles. Our CSBP module uses a dense incremental strategy with rates of 1, 3, 6, and 9. The low rates preserve structural integrity of small objects, while the high rates capture long-range context like road networks and building complexes. For the decoder, our RASBP module uses microdilation rates of 1, 2, and 3 to re-aggregate local texture during upsampling, sharpening object boundaries and reducing misclassifications in shadow-occluded regions. Here, Multi-Scale Context Fusion Module, CSBP, is integrated at the bottleneck to capture global semantic information and adapt to the substantial scale differences between buildings and cars. The Multi-Scale Context Fusion Module, CSBP, Standard Atris Spatial Pyramid Pooling, ESBP, typically utilizes sparse dilation rates, e.g., R equals 6, 12, 18, to rapidly expand the receptive field. However, in high-resolution aerial imagery, this sparse sampling strategy creates a gridding effect, resulting in significant information blind spots where local pixel correlations are lost. This is particularly detrimental for small, discontinuous targets, such as closely parked vehicles, leading to missed detections or fragmented textures. To overcome this, our CSBP module employs a dense incremental dilation strategy, e.g., R equals 1, 3, 6, 9, low rates, R equals 1, 3. These preserve high-density sampling to maintain the structural integrity of small objects and ensure no pixel information is skipped. High rates, R equals 6, 9. These capture long-range semantic context, such as road connectivity and large building footprints. This sawtooth sampling design effectively eliminates blind spots while expanding the receptive field, ensuring the model captures both local details and global context without suffering from feature discontinuity. And Detail Enhancement Module, RASBP, is embedded in the decoder to perform secondary refinement during upsampling. This structural evolution aims to optimize both the feature extraction capability for multi-scale objects and the boundary reconstruction precision for complex urban textures. Detail Enhancement Module, RASBP. Most UNet variants focus solely on the encoder, neglecting the information loss inherent in the upsampling process. Bilinear interpolation or deconvolution often smooths out high-frequency details, causing blurred boundaries between distinct objects, such as building edges versus vegetation. Our RASBP module addresses this by embedding microdilation rates, R equals 1, 2, 3, into the first two layers of the decoder, D2 and D3. This module performs a secondary refinement on the upsampled features, reaggregating local texture information to sharpen object boundaries and reduce segmentation errors in shadow-occluded regions. For the loss function, we adopt a composite strategy combining cross-entropy loss and dice loss. Cross-entropy penalizes pixel-level classification errors and helps distinguish among the 5 main classes. However, under severe class imbalance, it tends to be dominated by majority classes like impervious surfaces and buildings, causing the model to underperform on minority classes. Dice loss, on the other hand, directly measures the spatial overlap between prediction and ground truth. It is less sensitive to background size and gives stronger gradient signals for small or irregular objects like cars and tree crowns. By combining these two losses with equal weight, the model achieves both per-pixel classification accuracy and region-level shape consistency. For evaluation, we report mean intersection over union, or MIOU, and average F1 score, both excluding the background class, following ISBRS benchmark protocol. Our experiments were conducted on a machine running Windows 10 with an Intel Core i5-9400F CPU and an NVIDIA GeForce RTX 3060 GPU. The deep learning framework is PyTorch 2.7.1 with CUDA 11.8 acceleration. For hyperparameters, we trained for 100 epochs with a batch size of 8, using the AtomW optimizer with weight decay of 0.05 and an initial learning rate of 1 × 10⁻⁴. All input patches are resized to 256 by 256 pixels. For data partitioning, we follow the standard protocol established by He et al. In 2022, using 11 training images and 5 test images for Vehingen, and 24 training images and 13 test images for Potsdam. Importantly, we ensure zero overlap between training and test patches to prevent data leakage and guarantee valid generalization results. The ablation study validates the contribution of each module individually. Using the original UNet as our baseline, we see an MIOU of 66.35% and an average F1 of 79.13%. When we add only CSBP, the MIOU jumps to 73.08%, with significant improvements in car detection, rising from 48.29 to 59.45% IOU. Adding only RASBP achieves an MIOU of 73.29%, with noticeable gains in low vegetation and tree categories. When we combine both modules in our final model, we achieve the best overall performance, MIOU of 74.33% and average F1 of 85.32%. Critically, the car IOU reaches 62.42%, representing a 14-point improvement over the baseline. This confirms that CSBP and RASBP provide complementary benefits that work better together than either module alone. This slide presents qualitative visualization results comparing the segmentation output of each model configuration on selected test patches from the Vehingen dataset. Looking at the baseline UNet, we can observe fragmented boundaries in vegetation regions, shape distortions in vehicle contours, and adhesion artifacts where adjacent cars are merged together. When CSBP is added, the vegetation regions become more coherent, and vehicle boundaries more closely match their true shapes. With RASBP alone, building edges and small features near boundaries show improved spatial continuity. Our final combined model, shown in the rightmost column, produces the most complete and accurate segmentation across all classes, with smooth vegetation boundaries, well-separated vehicle instances, and consistent building shapes that most closely match the ground truth annotation. Now let us look at the quantitative comparison against state-of-the-art methods on the Vehingen dataset. We compare against the original UNet, DeepLab v3+, UpperNet, and DANET. Our proposed model achieves the highest scores across all 5 classes. For MIOU, we reach 74.33%, compared to 66.35 for UNet, 67.16 for DeepLab v3+, 65.84 for UpperNet, and 65.14 for DANet. The most remarkable gain is in the car category, where our model achieves 62.42% IU, compared to only 50.30 for DeepLab V3 Plus and a mere 42.68 for DANet. This 7.98 percentage point improvement in MILU over the baseline UNet and 6.19 point improvement in average F1 confirms that our dual ASBP design provides a strong advantage, particularly for small object recognition in complex aerial scenes. On the Potsdam dataset, which features higher resolution and clearer boundaries, our model again achieves the best overall performance. We obtain an MILU of 78.67% and an average F1 of 87.6%, the highest among all compared methods. Notably, our building IOU of 86.11% outperforms DeepLab V3 Plus at 84.76 and UpperNet at 83.93. This improvement can be attributed to the RASBP module effectively preserving structural information during upsampling, resulting in cleaner and more complete building segmentation boundaries. Our tree IOU of 70.94% significantly outperforms DeepLab V3 Plus at 63.05, demonstrating that our context-aware CSBP module better handles the complex occlusion patterns from dense tree canopies in the Potsdam dataset. The consistent improvement across both datasets confirms the cross-dataset generalization of our dual-lock architecture. To summarize our contributions, this work proposes an improved UNet integrating the CSBP context fusion module at the bottleneck and the RASBP detail enhancement module in the decoder, together forming the dual-lock mechanism. Experiments on both ISBRS benchmark datasets demonstrate clear superiority over standard approaches. Our model achieves peak MILU of 74.33 on Vehingen and 78.67 on Potsdam, outperforming UNet, DeepLab V3 Plus, UpperNet, and DANet across all 5 semantic classes. The most significant improvements are for small objects. Car IOU improved by 14.13 percentage points over baseline, and tree boundary quality is substantially enhanced by RASBP refinement. Furthermore, the composite CE plus dice loss function effectively mitigates class imbalance, producing more stable and consistent detection across underrepresented categories. Looking ahead, we identify 4 main directions for future work. First, we plan to extend this methodology to satellite imagery, which presents additional challenges due to lower resolution and weaker small object signals. We will explore super-resolution reconstruction and more flexible multi-scale fusion strategies. Second, domain adaptation and style transfer techniques will be investigated to reduce the distribution gap between UAV imagery and diverse satellite sensors, improving cross-sensor generalization. Third, we aim to integrate satellite multispectral data with elevation products such as DSM, DTM, and LiDAR point clouds, enabling comprehensive tree crown delineation and supporting carbon stock estimation as a longer-term goal. Fourth, model lightweighting and cloud deployment will be pursued to enable the proposed architecture to be integrated into large-scale automated processing pipelines for practical remote sensing applications. That concludes today's presentation. Thank you very much for your attention. Our proposed improved UNet with dual-lock mechanism demonstrates strong performance in multi-class semantic segmentation of high-resolution aerial imagery, with particular advantages for small object detection and boundary reconstruction. This work is part of a broader research effort at Feng-Cheng University, supported by the National Science and Technology Council of Taiwan under grants NSDC 114-2221, E0 35-076, and 114-2420, H 006-004. We welcome any questions or comments you may have. Thank you.